Okay, guys. Good morning, everybody. I guess it's time to start. Can you hear me down there with the mic? Okay, cool. Thank you. Today the idea is to start discussing a little bit electron-phonon physics. Yesterday we had an introduction on maybe I'm going to go here on density functional theory and phonons, and today we're going to try to start putting down some of the concepts that we need to understand electron-phonon interactions. So the idea is that I'm going to basically give 3 lectures over 3 days now. The first one this morning is going to be very basic. We're going to only discuss the main ideas with very simple equations. And then tomorrow and after tomorrow, we're going to step up the difficulty, and we're going to move to many body techniques like quantum field theory methods for electron-phonon physics. So if you already know the things I'm going to tell you, don't worry, because it's going to be more difficult tomorrow and after tomorrow, and less known things. So let's get started. And what I would like to tell you basically is, first of all, so where do you see electron-phonon interactions in experiments? Then how do we understand electron-phonon interactions using a very basic elementary perturbation theory? And that's, for many things, it's enough. And then we will move to the electron-phonon matrix element. That's because this afternoon there will be some exercises to see, to calculate that quantity. So we need to be prepared to understand it. And then I will introduce a little bit the problem of integration, the Brillouin-zone, and the Wannier interpolation, because after this there will be lectures and tutorials on Wannier functions. And then a couple of words about electron-phonon coupling constant that you will see this afternoon in tutorials. And then I guess a question that comes over and over again when we discuss electron-phonon physics is, what is the relation between perturbation theory and molecular dynamic simulation, for example, okay? So let's get started. And I guess the idea, the first question is, so why do we have electron-phonon interactions when we perform calculations? Where are they, and how do I see them? I guess the starting point can be the Kohn-Sham equations that we seen yesterday with Paolo Giannozzi. So he introduced density functional theory, and the bottom line was that for practical calculations, we want to solve a Kohn-Sham equation, okay, which has this kind of shape. So kinetic energy, potential energy, and then eigenvalue here. So the question is, can we use that to start understanding the notion of electron-phonon interactions? First of all, this is really a question of where are the nuclei in the story, because electron-phonon interaction is the interaction between electrons and the vibrations of the lattice. So where is the lattice in this equation? In practice, here I don't see the lattice, but if I go through a cycle of self-consistency, I know that I need to evaluate these wave functions once somebody gives me a potential. Then I get the density by squaring up the wave functions of the occupied states. And then I plug the density into a self-consistent potential, which has essentially the hard rate repulsion between electrons, and then the exchange correlation potential, which are both functionals of the electron density only, okay? So the question is really, where are the nuclei? Where the nuclei appear in this term, which is basically the attraction, the Coulomb attraction between each nucleus and each electron. So in this case, the tau sub k is the so if you look on the side, the tau sub k is the position of a nucleus, okay? So in this case, I'm putting just the bare Coulomb potential, but in practical calculations, we're using pseudo potentials, as we've seen yesterday. So the point is that if we don't know anything, we would say that the only dependence on the positions of nuclei is here. But if you look at this expression, you realize that actually this goes back into the self-consistent equation, and therefore at the next step, the solution will embed some dependence on the coordinates in the wave functions and in the energies, okay? So really the entire problem is dependent on the nuclear position, so both energies and wave functions and then charge density. So now let's put together what I just said. The idea is that the self-consistent potential is basically, in practice, apart from theories and apart from formal concepts, is very simply a parametric function of the nuclear coordinates. And you see that if you do a DFT calculation and you place, I don't know, silicon with atoms at equilibrium, you get certain eigenvalues. If you move an atom, the eigenvalues are changing. So that's the very simple statement of dependence of the potential and everything else on the coordinates. So now the idea is that if you are in a solid far from the melting point, you can assume that the nuclei are moving away from equilibrium by just a little bit, okay? So what people do is to perform a Taylor expansion of this object in terms of the atomic displacement, just to see what can happen, okay? So since there are many nuclei, one should perform a Taylor expansion with respect to all the nuclear positions and all the Cartesian coordinates. So if I were to write all these things, we would have giant equations, but we have a very simple concept, so there is no point of just putting all the indices down. So for now, what I'm going to do is to write derivatives by only considering one atom and one Cartesian direction, okay? So the transposition of that to many atoms and many directions is kind of trivial. So there is no point of bothering with all the indices. So in practice, if I perform a Taylor expansion on this object, I get the self-consistent potential at equilibrium. Then the first derivative times displacement, second derivative displacement squared, and so on. In practical calculations, whenever you discuss electron-Phonon interactions, basically nobody has ever gone beyond order 2. So we always stop at the second order. You know, it is possible to go beyond, but the complexity is such that there are other techniques to look at that, okay? Now, if you look at this expression, essentially, this, the first term is the Kohn-Sham potential for the nuclei, which are, you know, when they are clamped at the crystallographic sites, okay? And everything else has to do with the displacement of the nuclei. So really, the electron-Phonon interaction has to do with these terms, okay? So everything that we discussed in terms of electron-Phonon physics has to do with the term in the yellow box. And that's pretty much it. So in terms of density functional theory, if we don't want to be too sophisticated, this is the starting point. So now I'm going to stop a second here. We're going to discuss where do we see electron-Phonon interactions in experiments, and then we will go back to this equation, okay? So first manifestation, just to look at some kind of fancy systems. These are two measurements on basically monolayer and bilayer molybdenum disulfide. These are 4-terminal experiments. And essentially what the authors of this work were looking at is the mobility as a function of temperature. That's the electron mobility. So you will have an entire lecture tomorrow on the mobility, but for now, let's just say that it's the coefficient of proportionality between the average velocity of the electrons and the electric field applied to a system, okay? So that tells you how fast electrons can move in a system after you apply an electric field. And the important observation is that the mobility depends on temperature quite strongly. So in this case, it goes from maybe 200 centimeters square volt seconds at low temperature to maybe 20 at room temperature. So there is a change of a factor of tenfold, okay? And this is a manifestation of electron-Phonon interactions, okay? So we will look at that a bit later in detail. Another manifestation, which actually is pretty important for applications, is optical absorption in semiconductors with an indirect bandgap. So these are just an example of the solar cells of silicon. You might know that silicon solar cells are the majority, dominant majority of solar cells in the market. And the interesting bit is that silicon is an indirect gap semiconductor. So if you perform a band structure calculation, so if you go back to the exercise of yesterday and you look at the band gap, well, that's a DFT band gap, so it's a bit too small, but if you do something more accurate with GW, for example, you will see that the direct band gap of silicon is about 3 electromoles, okay? So that means that if there were no phonons, there would be absolutely no absorption in silicon below 3 electromoles. So that's the absorption coefficient, and what you can see is that instead, below 3 electromoles, there is quite some absorption here, and in particular, this coincides with the visible spectrum. So this is what is called the indirect Phonon-assisted optical absorption, and this has to do with electron-Phonon interactions. Actually, to be precise, it has to do with the quantum zero-point motion of the nuclei. So if there was no quantum zero-point motion, there was no electron-Phonon interactions, silicon will be pretty much useless for solar cells. Now, this is a more fancy example. This has to do with superconductivity, so we'll have some discussion on superconductivity on Friday. This is, let's say, the latest breakthrough in the field is basically a superconductivity in compressed sulfur hydrides. In a superconductor, the idea is that below a certain temperature, the resistivity, the electric resistivity drops to 0, so completely 0. And that's quite important for many applications. So in this case, people measured the critical temp, so basically the resistivity as a function of temperature, and essentially here you see that it drops to 0 at about 200 Kelvin. So that's quite important. And the reason I'm showing you this is that in a class of superconductors known as conventional superconductors, the mechanism of superconductivity has to do with electron-phonon interactions, okay? In this case, the way to confirm that it has to be with electron-phonon interactions is to do isotopic substitution experiments. Let me explain what this is about. Yesterday, you've seen in the lecture of Paolo Giannozzi that the vibrational frequencies, so the dynamical matrix, has 1 over square root of the masses in front of it, okay? So that means that the phonon frequencies are proportional to 1 divided square root of the mass of the atoms. So that means that if you take a system, a solid, and you do isotopic substitution, you don't change the chemistry, but you change the masses of the atoms, and therefore you change the vibrational frequencies. So in this case, what they did is to replace basically hydrogen by deuterium. So you double the mass of the nucleus. So you change the vibrational frequency by a factor of square root 2, okay? And accordingly, the critical temperature decreases approximately by 50% here, okay? So this is typically the smoking gun of an electron-phonon mechanism in superconducting samples, okay? So that's one of the other examples that are important. This is more recent. It's so that's basically a ball and stick model of a perovskite. So it's this object with octahedra connected in a corner sharing way. This is called a hybrid perovskite because there are organic molecules in the middle. And inside the octahedra there is lead, and then out on the corners there is iodine. So this object have been studied a lot in the area of photovoltaics. And the only reason I'm showing this here is that you can measure the bandgap, for example, or something which is close to the bandgap by using photoluminescence. Means you excite about the bandgap with a laser, and then you look at the emitted light. So what you look at here is basically the peak of the emission as a function of temperature. And what you can see basically is that it increases with temperature. So this increase with temperature of the emission line has to do, again, with electron-phonon interactions, okay? So that's another example. And then I think this is my last example for experiment. This is basically a ARPES experiment. So ARPES means angle resolved photoelectron spectroscopy. We will see some more details about ARPES after tomorrow, but for now, let's just say that it's a very sophisticated tool to measure band structures, okay? So what you need to imagine here is that this is a portion of the valence band, so basically a portion of the occupied states, band structure in the occupied states of magnesium boride, which is a metal. And if you perform DFT calculations, probably you cannot see it, but there is a dashed line. So the DFT calculation will give you a band structure which is straight near in this energy range, near the Fermi level. But if you perform an experiment, actually there is kind of a wiggle here. So there's a change of slope, and then it goes back to being straight. So this change of slope is a change of the band velocity, okay? So the electron velocity, and that's also a change of the electron mass. So since the slope is lower, this means that the electrons have a smaller velocity and heavier mass. So this phenomenon is called mass enhancement in metals, and this is, okay, again, a manifestation of electron-phonon interactions. So most of the things that I just discussed is something that we now understand pretty well, and they can be calculated from first principles. So that's a bit these are some of the experiments that we are interested in trying to understand and maybe predict. So let's go back to now the equation I gave you earlier. So I told you that basically to define electron-phonon interactions in DFT, we basically look at this perturbation Hamiltonian. So change of self-condensing potential with respect to position times displacement plus second-order derivative times displacement square. Now, when you have a perturbation, okay, you have a perturbing potential. So what do you do with that? Well, if you go back to your quantum mechanics textbooks, you know that as soon as there is a perturbation, people tell you, well, you need to do perturbation theory on top of that, okay? So that's what we're going to discuss now. And really, the simplest level of perturbation theory, so something that nobody even bother give me a name to, is called Rayleigh-Schrödinger perturbation theory. So these two names, are just from those that did it for the first time. In fact, this has been done in the very, maybe second or third paper by Schrödinger when he made the quantum mechanics. So the simplest thing that you can do is to look at how the eigenvalues of the system change due to this object. So we know that the energies change, the change in energy is given basically by the sandwich of the perturbation here in between a given quantum, the same quantum states on the left and the right. So here I'm just putting only one of the terms because I'm lazy. I don't want to just write a giant equation. But whenever you have a perturbation, you basically take the expectation value of that perturbation on your quantum state, and that's the change in the eigenvalue, okay? So that's something that you find in any textbook. Actually, if you write perturbation theory in Wikipedia, you find all these equations. I mean, there is nothing really new. But that's quite interesting because this means that we already have a recipe to look at changes in the eigenvalues coming from electron-phonon perturbation. There is something else that you find in the same book chapters, perturbation theory, that is what is the change of the wave functions. So it's just slightly more difficult. So this is a diagonal matrix element. So this is non-diagonal matrix element between two different states, then divided by the energy difference between these two states, and multiplied by the wave function of these states over which we are doing the summation, okay? So that's just a standard recipe. Oh, just because I'm lazy. I mean, I don't want to have a giant equation. I mean, I could have written everything. It's just that it's difficult to read it and absorb it. I mean, but yeah, in the right, if you were to do everything carefully. Yeah, it is there. We will see it in a second, actually. So this is basically about static perturbation theory. It means that in this in this concept, I basically displace an atom by an amount u, and then I have this change in the potential, and then I look at what happens to the eigenvalues and wave functions. I can do something slightly more advanced, which is basically the next chapter in the book on quantum mechanics, and that is to say that my displacement is not just a number, but it's something which is changing with time, like periodically. So, for example, I can move an atom, left and right, like a cosine function as a function of time. And clearly, in that case, I cannot use the static perturbation theory to use time-dependent perturbation theory. And in that case, the recipe changes slightly, but it's also quite simple. Basically, what I can calculate when I have a time-dependent perturbation which oscillates, let's say, with a frequency omega, I can calculate the rate of transition from a given quantum state to another quantum state arising from this kind of perturbation. So this rate of transition is called the Fermi-Golden rule, and involves the square matrix element now of this perturbation, and then a Dirac delta function which can be understood as a way to ensure energy conservation, but it's really just a mathematical result. So this would be the difference in energy between the two states, and then the frequency of this oscillation. So these are basically three results which are really don't require any understanding of density functional theory or electron-phonon interaction. That's really something that we learn in the first course on quantum mechanics. But it turns out that actually those three things are already a lot in terms of performing practical calculations. So in fact, they probably with that you can perform most of the electron-phonon calculations that you need. Now, what I didn't tell you here is that so this is basically a static perturbation, and this has a derivative and times displacement, but I never say what is the displacement, okay? So in a sense, this is not really describing electron-phonon interaction. It's just describing what happens if I move an atom. So we start talking about electron-phonon physics when we specify what is the motion of this atom, and when this motion is essentially some kind of vibration. So the idea here is to try to understand what do we need to place here for this parameter, because if you leave it free, I mean, you can get any number. So this variation is proportional to the displacement. So if you get, if you place a big displacement, you get a big change. I mean, so what do we place there as for the displacement? So in principle, we have a displacement for each atom in the system and for each Cartesian direction. Okay. Problem is that if you're looking at a solid, you have a lot of atoms. And in an actual experiment, all the atoms are moving around, they are doing whatever they want. So tracking all of this is nearly impossible, and nobody really cares, because it's too much information and it's not very useful. So what people are interested in typically is to know what is the average displacement at a given temperature at thermodynamic equilibrium, okay? So that's one possibility. The other possibility is to look at non-equilibrium dynamics. That's another possibility. But essentially, it's setting some kind of conditions that you want to look at. So in this lecture, we're going to look only at thermodynamic equilibrium because it's a bit easier. And the idea is that if you are at thermodynamic equilibrium, and if we make the harmonic approximation, so the system, I mean, the atoms move in a parabolic potential, like you've seen yesterday, in density functional perturbation theory, the good news is that all these displacement can be mapped into a set of non-interacting, so independent harmonic oscillators, okay? So harmonic oscillators means that really the displacement of each atom can be actually translated into the same problem as that of a mass attached to a spring, which is displacing around this end. And at this point, really, the kind of the mathematics becomes really the mathematics of the harmonic oscillator. There is not much more than that. So the difference between a single spring and phonons in a solid is that one spring is one spring, and in a solid you have a number of phonons equal, so a number of vibrations, which is equal to the number of atoms times the number of Cartesian directions, okay? So yesterday we looked at dynamical matrices. Okay, I don't know, in silicon you have 2 atoms per unit cell, you have 3 Cartesian coordinates, so you have 6 vibrational modes, okay? So you can describe the motion of the atoms in terms of those 6 independent modes of vibration. So each of these modes is mathematically equivalent to a single spring. So if you want to describe the thermodynamics of a spring, the good news is that if you are in a classical system, so no quantum mechanics, you can just use the equipartition theorem, and that tells you that basically the mean square displacement, so U squared, as a function of temperature, is something which has a very simple expression, is basically proportional to temperature, okay? And I'm showing you the mean square displacement simply because the displacement, the mean displacement U, okay, the first order, is 0 because in a harmonic system, the potential is parabolic, so it's an even function. So the probability of being on the left is equal to the probability of being on the right, and the mean displacement is 0 in average, okay? So the first function which is non-zero as a function of temperature is the mean square displacement. And that's basically a function which grows linearly with temperature. So there is nothing really difficult about that. So now the question is this enough for calculations? For some calculations it is. For some it is not, and I'll give you an example in a second. So in some cases you want to consider the average of this displacement using quantum mechanics, and that means that basically you take the eigenvalues, so the quantum harmonic oscillator, you perform an average of displacement, you average over temperature, and the result actually is slightly more difficult, but it's still quite simple. It's basically something which is proportional to 2n plus 1, where n is the Bose-Einstein distribution, okay? So this blue expression is given by this line, all right? So, I mean, if you think about it, I'm not saying anything new in the sense that if you go again to Wikipedia and you look for the quantum harmonic oscillator, all these things are there. I mean, also the maths are there, so there is nothing really new here. We're just trying to piece things together to understand how to deal with electron-phonon physics. So actually, this plot, it seems very easy, but it has a lot of important physics inside. So the first thing that we notice that basically the mean square displacement of the nuclei, I mean, if you go to, let's say, high temperature, it goes linear. So actually, it goes asymptotically to the classical result. So that's consistent with the fact that we think that the idea that if you go to a high enough temperature, you know, a quantum system becomes increasingly more classical. The difference is really at low temperature, where in the classical case, the square displacement goes to 0. So basically, the nuclei don't move anymore. They're just stuck into a point. While in the case of the quantum displacements, this is flattens up and essentially goes into a constant, meaning that even at 0 temperature, the ions are moving a little bit, okay? Now, the interesting bit is that I just told you, high temperature, low temperature, but this doesn't mean anything until you specify what you mean by high and low. And really here, the difference is given by this intersection point. So this is basically the point where the quantum curve hits this vertical axis. So if I draw a horizontal line, and I look at the intercept with this the classical result, I get this point, which gives me basically half h bar omega. So that's the point more or less where these two curves start deviating. So really, alpha h bar omega is the characteristic temperature really of the system. So let me make an example. In the case of the perovskites I showed you earlier, the characteristic vibrational frequency, the important one, is about 10 millivolts, let's say 13 millivolts. This has to do because with the fact that there is lead and iodine, which are very heavy. So 10 millivolts, let's think about room temperature, that's about 25 millivolts. So in this plot, so if this is 10 millivolts, room temperature would be about here. So in that system, basically, if you use quantum mechanics for the nuclei or classical mechanics, the result is going to be very similar. Not much difference. Now let's look at another system. If you take, for example, graphene. So graphene, the most important, let's say, vibrational mode is about 200 millivolts. So that's about, let's say, 10 times room temperature, meaning that if this is 200 millivolt, in graphene, room temperature is about here, okay? So basically, in graphene, we are saying that this is the actual displacement in the quantum system. And if you do a classical approximation, you get it very wrong, okay? So this is to say that, for example, graphene, in terms of nuclei, is very quantum. And those lead perovskites, in terms of nuclei, are very classical, okay? That's a bit a way to think things. Now, the point is that we don't really care in the sense that when we can do these calculations, we can try both. And clearly, the most accurate is the quantum case. But sometimes people want to find, whether, the effects come from, quantum fluctuations, or it's really just a classical effect, and that's the way to understand it. And, just in terms of terminology, so this little kind of step here, it's called the quantum zero-point fluctuation of the nuclei, okay? And whenever an electron-phonon effect has to do precisely with this object, we talk about quantum zero-point normalization coming from electron-phonon interactions. So that's all that we need to know in practice. So and then you need to remember this kind of shape, which is flat here and then goes linear, because I'm going to show it in a second. So now, now we know how to deal with the mean-square displacement. What I want to show you actually is that this very basic perturbation theory can be used to do quite useful things. In particular, if I take the thermal average of the change in the eigenvalue, I can calculate temperature-dependent band structures. If I take the thermal average on some functions which contain the change of the wave function, I can calculate, for example, Phonon-assisted optical absorption. And if I take some thermal averages of the scattering rates, I can obtain transport coefficients, like, for example, mobilities, okay? So we will not go too deep into this, because we will have lectures about that in the next few days, but I just want to give you a flavor of what happens. So let's look at the first bit, so how you can get temperature-dependent, let's say, eigenvalues. So I told you that we need to take this object, so the change in the eigenvalue is this sandwich, and then that basically is proportional to displacement. So what we need to do here down is to take a thermal average of this displacement. However, I told you that the potential in the harmonic approximation is symmetric, and therefore this first term goes to 0, because this averages to 0 at the end. Doesn't mean that the change in the eigenvalue is 0. Just means that we need to go to higher order in perturbation theory. So this is just the first order perturbation theory. This is the same perturbation, but to second order in perturbation theory. So in this case, it's proportional to the square displacement, and if you take the average, it gives something that depends on temperature. And now the term that you asked about before comes back, because we have another term, which is the second order expansion of the Hamiltonian in terms of displacement, which also is proportional to, gives a term proportional to u squared, and that can be basically treated as using first order static perturbation theory. So if you put those two things together, basically, and you group them, and you take out the u square, and then you take the thermal average, that's basically the way to calculate changes in the eigenvalues which are dependent on temperature. So this, in the quantum case, becomes 2n plus 1, and basically it's an object which gives you essentially the main recipe to calculate temperature-dependent bands today. So I will not give too much more detail about that, because on Thursday there will be Xavier Gonz essentially dedicating the entire lecture to the technical details involved in this kind of calculations. But if you are getting lost and things seem a bit getting out of hand, this is really the only, the starting point, that the main concept. There is not much more than that, okay? So to give you an idea of why this generates temperature-dependent, band structure, for example, let's just look at a very simple example. I want to concentrate on this object, okay? So let's forget that, just because I want to make things simple. And what you can notice here is that there is a quantity which is positive, and then some denominators. So if I look at the band structure of a semiconductor, so just very simple, valence band, conduction band with a band gap. Maybe let's look at the bottom of the conduction band. So if I sit here, basically, in this expression, I had basically the n. So n is also the first of the two eigenvalues. So this means that here, if I look at the bottom of the conduction band, the first eigenvalue is the conduction band bottom. Now, if you look at this denominator, basically, the largest contribution will be from states which are very near the conduction band bottom, simply because it's a very small number, so they're going to lead to large. So if you do 1 divided by a small number, it's a large number, okay? So the most important contribution will come from terms which are close to this conduction band bottom. But since it's the bottom, by definition, all the states are above it. So that means that this number is a negative number, okay? So this whole term is negative. And there was a u square which increases with temperature. So that means that the conduction band bottom, as a function of temperature, will start shifting down, okay? For the same reason, the valence band top here, I can do the same observation. If I'm sitting here, the states which are most important are those below it, and therefore this number is positive. So the valence band top will try to go up with temperature in this simple example. And if you take the difference, you find essentially a band gap which depends on temperature. And typically, at least for the simplest semiconductors, the band gap goes down with temperature, okay? And if you remember the curve I told you about, the mean square displacement, this thing was flat and then going linear. So that's basically exactly the same shape, just in reverse. Essentially, you see the signature of that kind of dependence here in the dependence of the band gap. And I would like to say two other things here. The first one is that if you remember the example I give you for the perovskite, the photoluminescence, there the band gap was going up, okay? So there is no inconsistency. The only difference that here I'm making a very extreme simplification. So for a lot of simple systems, this is what happens. For some systems, the band gap has a different temperature dependence. That has to do with the fact that this term is not always negligible. So when you do a complete calculation, you need to look at everything, basically. Yeah.
Yesterday, when Stefano was explaining perturbation theory, okay, he said that the only thing which matters in the perturbation of the states, for example, the field state is the projection on empty states.
Yeah.
So then your argument would not hold, because the field state, if you take in this perturbative expansion only those which are on the other side of the gap, then the side which is beside the field.
No, I mean, I think that the argument was about the wave function, the change in the wave function. So this is the change of the eigenvalue. So that they're completely consistent, basically. So he was looking at the change in the density. So that's psi delta psi, this psi. And if you look at that, basically, there is only a connection between valence and conduction. So this is the change in the eigenvalue. So you cannot play the same trick, basically. So all the states matter in this case. That's the answer. So this is just to give you an example calculation. This is something again on the usual example of silicon. The black dots basically. I'm sorry. I mean, I wanted just to say something. I'm sorry for that. So in this expression, basically, this is the dependence using the quantum nuclei. So the average of the nuclear displacement using quantum mechanics. If you replace that by a classical approximation, okay, use a classical harmonic oscillator. In the same way, the displacement goes linearly with temperature. In this case, the band gap will go linearly with temperature, okay? That actually corresponds to a situation where you are moving atoms, for example, in molecular dynamics, and then you cool the system down. So you would expect the band gap in average to go, to change linearly with temperature. So the important observation here is that if you go to 0 temperature in DFT, you basically have nuclei stuck at this point. So the nuclei don't move. They basically T equals 0, classical nuclei. You just have point charges, in some crystallographic sites. So you are really calculating, let's say, a band gap or a band structure at this point, okay? The experiment is not looking at this, it's looking at this. So in practice, every DFT calculation, let's say at least in principle, gives you a band structure which is not the correct one in the sense that it corresponds to basically that point up there, but what we really should calculate is this point here. So this little change is called quantum zero-point normalization of the band structure. And I mean, it's a small number. That's why people don't notice. Typically, for many systems, is between 10, 50, 100 millivolts. But there are some exceptions. There are some very light systems like carbon and things like that where this number can be very large. Okay, so that's something to keep in mind. So if you want to do very refined calculations, that has to be taken into account. And that's an example for silicon. Basically, this is the black dots are experiments. So this is ellipsometry. So essentially, it's a measurement of the imaginary part of the electric function, and the blue line are DFT calculations. Okay, based on this kind of techniques. So you can see two things. First is that DFT gives a reasonable agreement with the experiment, and second that we kind of understand what is going on. Things seem to fit with what we expected. Okay. So in this case, the change of band gap with temperature is quite small. So we go from, I don't know, 0.17 to 1.07, so it's maybe 0.1 eV over 500 Kelvin. So that's not a very big number unless you are really looking at a very fine structure in these things. Now, I wanted to tell you something about the second bit, which is the Phonon-assisted absorption. And one may wonder, so why do we have how do we use simple perturbation theory to look at Phonon-assisted absorption? Actually, the answer is very simple. So this is the expression I gave you before, okay? So from any textbook on quantum mechanics I told you. Now we should remind ourselves of what is the expression for optical absorption. And I'm going to use the simplest possible expression, which is this thing here. So it's the imaginary part of the electric function. That's basically long wavelength limit, okay? It's essentially given by a sum of transitions between the valence and the conduction, okay? This is the optical matrix element, so it's what you see in textbooks called as a Hamiltonian electron radiation. In this case, I'm using the electric dipole approximation using in the momentum representation. So it's just a simple way of doing things. And this is our delta functions which take care of energy conservation between the valence, the conduction, and the photon energy, okay? So in this case, h bar omega is the photon energy. So that's an expression that is, it's basically the lowest level approximation you can do for optical spectra. And that's something that actually is implemented in the post-processing tools of Quantum-Espresso as epsilon.x, to some, I mean, we are close. It's not exactly that, but it's similar to that. So if you run epsilon.x from Quantum-Espresso, you get basically something which corresponds to this expression. That's for static nuclei. Now, if I take into account the change of the wave function coming from the displacement of the nuclei, what I have to do is to replace the valence and the conduction here plus by something which is modified by this amount, okay? So what I need to do is to insert this object inside this, inside this matrix element here on the left, inside the valence on the right. So here we have two terms, the unperturbed plus the perturbation on the left. Then I will have the same thing, unperturbed plus perturbation on the right. So there are basically 4 terms, and this goes to the square, so it's basically 8 terms entering the expression. So I'm not going to show you all of the 8 terms, but each of them basically looks like this guy here. So you can see where it comes from by maybe imagine that you have this electron-photon matrix element times electron-phonon divide the denominator. So it's electron-phonon divide the denominator, okay? So these things just come from doing some math on this expression. There is nothing really complicated. So the interesting bit here is that if you now follow this chain, valence, intermediate state conduction, that should remind you of this expression that you see in every textbook that basically tells you that if you want to perform, if you want to calculate optical absorption in an indirect gap semiconductor, since you need to conserve crystal momentum, this is basically, so this transition would be forbidden in the absence of phonons, but you can do basically you can go around it by having this state to be promoted to the conduction. Then there is a scattering via phonon into the bottom of the conduction, and therefore you can access this transition by combining basically a photon and a phonon, okay? So that's basically the basic mechanism of indirect absorption. If you want to do a more sophisticated theory, you would have also the phonon frequencies here in the denominator, and things can be done a bit better. So on Friday morning, there will be a lecture by Emmanuel Kupakis on indirect absorption, so you will see more details about that. But let's say the basic mechanism is pretty much this one. So if you try to calculate that for, again, our usual suspect, so this would be the optical absorption measured for silicon. If you use, again, epsilon.x for silicon, and you do a scissor shift just to get a gap which is decent, so I don't know, maybe it's 0.6 in DFT, you want it to be 1.1, okay? So you do some kind of GW corrections. And you use the epsilon.x, you get this red line, okay? So as I told you at the beginning, basically you can capture direct absorption above about 3 electrovolts, but you miss completely the indirect absorption. And if you use this kind of ideas that I just described to incorporate electron-phonon interactions, things improve quite substantially. So you get the blue line, which actually reproduces the indirect absorption, okay? So what I just told you is not something just for fun. It's something that can be used for explicit calculations. And then I want just to say a couple of words about the third thing that I mentioned. So that's scattering rates. There will be an extensive discussion of this tomorrow by Samuel Ponce. but I just want to give you a basic idea. So I told you that if you have atoms moving and you want to use time-dependent perturbation theory, what you can use is the Fermi-Golden rule to look at the scattering rates. So that's the rate to go from one state to another state, okay, due to electron-Phonon interactions. So we can do something a bit more complicated, which is simply to say what is the rate for an electron not to go to just another state, but to go anywhere, okay? So that's just the sum of the transition rates to any other possible state. So that's basically this number is the sum over all the final states of these transition rates, and that's basically called the reciprocal or the relaxation time of an electron. So why that is important? That is important because this quantity basically enters an expression for the mobility. I will not give you details about that, but what I want to just see is that the mobility is basically an average of these relaxation times weighted by some factors, and is probing only the states near the conduction band extrema. This exponential basically is saying that this average is only carried here and here if you're in a semiconductor, okay? So the idea is basically that if you can access the transition, so the scattering rates, you can obtain these kind of expressions, and then this, if you remember your solid state physics 101, you should remember that that is basically the something similar to the Drude formula. So if you open Kittel, like page 8, that's basically the first thing you find. Okay, so there's nothing really too complicated. Now, to perform a practical calculation of this effect, it takes some time, and it's quite difficult because there are many technicalities. So these technicalities will be discussed tomorrow. So this is basically the concept that I wanted to convey. You noted that basically I've been talking about matrix element where the electron is the index is just a number, so a discrete index. There is a displacement with respect to, so the change with respect to one single coordinate. The 0-point displacement was involving just one mass and one frequency. So what you've seen yesterday is that there are many masses, there are many frequencies, there are many branches of phonons and bands. So really, when we study electron-phonon physics, so it's just an example of gallium arsenide to kind of make contact with what you've seen yesterday. You cannot just describe these properties in this very simple representation. You need to take care of the fact that we have bands, we have crystal momentum of the electrons, we have branches for the phonons, we have crystal momentum for the phonons. So these objects are quite more complicated in practice, okay? So what I did so far is just to look at the concept, but I did not look into the details of the calculations. So since today, this afternoon, you're going to look at the first calculations of matrix elements, I want to tell you a bit about how they look like in real life. So this is basically, I would say, the standard expression of a electron-phonon matrix element within density functional theory. So what you see basically is a object. First of all, how much information is here. So this is basically something which depends on two band indices, M and N. Then there is a phonon branch index. And then there is the crystal momentum of the electron and the crystal momentum of the phonon. So basically there are three discrete indices and two continuous variables. So you can imagine that to describe that, you need a lot of disk space, okay? So, or memory. So that's really a very large amount of information. So in a real calculation, that's actually one of the problems, that you have to deal with a lot of information. How is this defined? Basically, these two things on the sides are very simply the block periodic part of the Kohn-Sham wave functions, okay? This band index, this wave vector. So K, for example, band index, the wave vector K plus Q. And what you see in the middle is the change of the self-consistent potential, this time not with respect to the displacement of one atom, but with respect to the displacement of every atom according to a given vibrational mode, okay? So that means that if you calculate the dynamical matrix like we seen yesterday with Stefano De Gironcoli, that defines the normal modes, and basically this change corresponds to the variation of the potential according to a certain normal mode, not a given atom, okay? So this object now, it's quite complicated. So if we want to write it explicitly, it contains quite a lot of information. So first of all, I told you that we were starting to look at the 0-point displacement being h bar divided twice the mass and the frequency. In a real calculation, there is a mass for each atom. So m sub k, so where k is the atom. Then there is a frequency for each vibrational mode, so that becomes a little bit more complicated. We need to tell the atoms in which direction to move. So basically, we take into account the phonon polarization. So this is simply the eigenvector of the dynamical matrix. So yesterday you see some dynamical matrices, you diagonalize them, you get eigenvectors. So those eigenvectors are these quantities entering here. And then there is the change of the self-consistent potential with respect to the displacement of each atom in the cell, okay? So this is the way to compute this object, and I should also say that in Quantum-Espresso, basically the derivative is not taken with respect to this displacement, but there is actually some kind of symmetrized displacement that I use to make things a bit more convenient from the point of view of calculations. So the actual calculation is quite complicated, and but what I would like to emphasize is that all these changes in the potential also involve a periodic modulation, which essentially allows you to access wavelengths of the vibration which go beyond the unit cell, okay? So this is the reason why we use density functional perturbation theory for most of these things, simply because you need to consider phonons with any crystal momenta. And if the wavelength corresponding to a crystal momentum is beyond, so it exceeds your unit cell, either you do a supercell calculation, but for electron-phonon physics, that becomes almost unfeasible. It's very, very difficult because the computational cost is excessive. Or you use density functional perturbation theory to access any wavelength by performing still unit cell calculations. Now, I want to say a couple of things about some of the problems that exist in these calculations. And this is just an example because this essentially will introduce some of the things that we need to do today and tomorrow in the tutorials. This is an example expression for the lifetime of an electron in a metal. It's very simplified. It's using an adiabatic approximation. So that's not the most accurate way to calculate a lifetime. So tomorrow we will do a formal theory of lifetimes, and we will define what they mean exactly. But for now, I'm just showing this here because I want to make the point that if you want to calculate this object, first of all, you have an integral over the phonon wave vectors in the Brillouin-zone, okay? Integral means that we need to sum over a lot of phonon wave vectors. And typically, since there is delta functions here, so Dirac delta functions, in order to get a number which is converged, meaning that it doesn't depend anymore on the sampling accuracy, you need typically something of the order of 100,000 wave vectors. So that's not a big number if you're doing simple maths, but since you need to perform one DFPT calculation for each wave vector, that can become essentially impossible for most systems, okay? So that's where the complexity comes from. So the other thing is that, for example, if you want to study, transport properties, like the mobility, I told you that they depend on the lifetimes of the electrons, but not just on one electron. So you need to basically average over all the electrons that you need, and therefore you need to repeat this operation for a lot of electrons, so for a lot of wave vectors. So that means really that you need to be able to compute this matrix element for a lot of wave vectors, okay? So this is really difficult. And the way that has become established now to do these calculations efficiently and accurately is to go via Wannier functions. And that is the reason why you will have a lecture in a bit and the tutorials later today about maximally localized Wannier functions. So I don't want to say much about this because there will be the experts following me, but the main idea is basically that in the same way you can describe electrons using block functions or Kohn-Sham states, which are periodic, you can also try to perform a unitary rotation, so a transformation of these states, to obtain new functions with the property that are localized, that these functions are localized. So for example, if you take a block function, which is, let's say, some atomic-like orbitals modulated by a wave, that would be the block wave, you can try to do this transformation to extract, basically, the atomic characters of these objects. And the most important thing of this kind of Wannier function is that you can go reversibly from the left to the right, without any problems, meaning that basically you don't lose information when you do this transformation, okay? So it's just another way to represent the electronic structure of the system. So why I'm telling you that? The reason why I'm telling you this is that in the electron-phonon matrix element, I told you that there are 3 bits. There is an electron, changing the potential, another electron. So if you imagine transforming the 3 of these objects into a Wannier representation, you might hope to get into a description where the matrix element corresponds to an integral between 3 objects which are localized, so maybe a first function, the potential, and then a second function. So if these objects are localized, it means that maybe if they find each other, far away from each other, where a function is non-zero, maybe the other functions are zero, and therefore the integral vanishes, okay? So the idea is that when those things are far away from each other, the matrix element is zero. So actually, it's very good news, because that means that probably you don't need to calculate hundreds of thousands of matrix elements. You need only to calculate those that are close to each other, okay? So the way to formalize this statement is basically that one can write down a unitary rotation between the matrix element in the block representation and the Wannier representation. So that's basically this expression, which is somewhat a Fourier transform, okay? So it's as simple as a Fourier transform. And the idea is that you can go back and forth from left to right. So you remember yesterday, Stefano De Gironcoli told you that if you want to do phonon dispersions, you can calculate phonons on a grid, let's say 4, 4, 4 or something like that. Then use this subroutine called Q2, this script called, code called Q2R.x. You get the force constant in real space, and then you interpolate back with maddin.x to get the dispersions in the Brillouin-zone. So we can do exactly the same with the matrix element, okay? So that's basically the idea. You do a calculation on a small grid, let's say 444 or 888. Then you go into real space, and then from that you interpolate back on any point. So in essentially, this technology is what we're going to use tomorrow in the tutorials. And by doing that, essentially, the advantage is that you perform a few calculations. Okay, they can be a bit expensive, but they're affordable. But then you get a very good sampling in the Brillouin-zone. Okay, can you say which part would be? Yeah, so basically the idea basically is that if you have a Brillouin-zone and you have a grid, okay, what you can do is to go to real space. So suppose you have 1, 2, 4 points here, so 4 by 4, that will correspond essentially to a supercell, which is 4 by 4 in terms of basically it would be 4 by 4 times the unit cell, essentially. So what is happening is that if you start from a calculation of matrix element where you get information for, or a grid of 4 by 4 in real space, so this object will correspond to a grid which essentially go to a real space kind of volume, which covers, which extends over 4 times 4 replicas of the unit cell. So what is going to happen is that in that representation, so maybe some of the wave Wannier function will sit in here, and this is the change of the potential. So that is not going to be 0. But sometimes there will be one Wannier function here, one Wannier function here, and the potential may be here. So if you do an integral between this object, and this object, there's going to be 0. So in practice, what happens is that this is what you calculate, and then one makes an assumption that if I have another function here, then matrix element, I say this guy is going to be 0, and then I interpolate back. So essentially, it's a Fourier transform where you pad with zeros everything which is outside of your domain, and you go back. So clearly, one has to check for convergence and things like that. But I guess the bottom line is that with this expression, what we are just saying is that there is really no need to calculate so many matrix elements because they already contain a lot of information which you can see better if you work in a Wannier representation. That's what we are saying, essentially. So this is a way to retrieve the information without performing too many explicit calculations, as simple as that. Now I want to just tell you in 2 minutes a couple of words about some of the names that you will see this afternoon. So there is an object which is called the electron-phonon coupling constant. I'm sure that all of you have heard of the term electron-phonon coupling. A lot of people, when they talk about the electron-phonon coupling constant, they really mean this number, okay? So let me tell you what is this number. So that's basically the Fermi surface of copper, just an example. So the electron-phonon coupling constant is basically, at least as it is defined in the calculations you see in Quantum-Espresso, is basically an average of the matrix element for every pair of electrons on the Fermi surface, okay? So as simple as that. So this is basically the definition. Now, this quantity, what you can see is that it's the square of the matrix element, that's an energy square, divided the energy of the phonon, so there's an energy. That's density of state at the Fermi level, that's 1 over energy, so this number is dimensionless, okay? And typically, this thing is only defined for metals. So that's the important thing, okay? So when we talk about the electron-phonon coupling calculated in Quantum-Espresso, that has to do with metals. That's an important thing. We should not confuse with semiconductors, insulators, or other things. this thing, I just say that it's an average of the Fermi surface. Typically, it takes a number, a value between 0 and 2 if when you hear that some systems have strong electron-phonon coupling or small electron-phonon coupling, typically people mean that if this number is between 0 and 0.2, 0.3, it's very weak coupling, and if it's about that, it can be moderate coupling. If it's about lambda equal 1, it's a large coupling, strong coupling. But this is really just historical, people have been using these terms, but it's more a matter of, it's very qualitative. There is nothing really, formal about that. Historically, this quantity is important because if you look at the BCS theory of superconductivity, it turns out that if you simplify as much as you can and you look at an isotropic metal, elemental metal, like an electron gas, so you basically do the simplest thing you can, you discover basically that the critical temperature, the superconducting temperature, is proportional to exponential of -1 over lambda. So clearly, by estimating this parameter in some way, you can get a feel of what the critical temperature would be. So that's the main historical origin of this object. And the other thing is that in elemental metals, this number has to do with this massive normalization. If you remember magnesium diboride, I told you that RPS experiments see a change in slope. So that's the electron becomes heavier. So that can be calculated using this number. 1 plus lambda is the change in mass. But again, this has to do with elemental metals. That is not for complicated systems, okay? So that's an extreme approximation. So the point is that we need to really use it with caution. So tomorrow, when we're going to do the many-body theory of electron-phonon interactions, we will see how similar quantities can be defined for other properties like optical properties, band structure of insulators and semiconductors and things like that, okay? But the number you're going to calculate today is for metals. That's the bottom line. Finally, I think I'll tell you in 2 seconds, one last thing is that what is the relation between perturbation theory and molecular dynamics? This is just an example of a nice calculation by another group about the band gap of this like perovskites, a function of temperature. So what they did is to do Karp-Parnell molecular dynamics, okay, of an object, a room temperature, and then they looked at the band gap at each molecular dynamic snapshot, okay? So that's a very intuitive way of looking at how properties depend on the temperature, for example. So what you can see here is basically that the band gap actually is fluctuating dramatically. Sometimes they change by 0.2 electromoles and things like that. And there are configurations where this band gap can change a lot, okay? So the question really is, do we need to, what is so how do we understand these numbers? So does a real physical system access values, extreme values of band gaps and eigenvalues? Well, basically the answer is no, okay? Because the only thing that matters here is thermodynamic averages. So I will not spend too much time on. The idea is that in molecular dynamics, what we are doing is looking at something similar to perturbation theory, but from another way, okay? So what we've seen so far is basically that if you take the eigenvalues, you can essentially do a parametric expansion in terms of the displacement of the nuclei. So that's, in 2 words, what I try to say today. And then in perturbation theory, what people do is to try to evaluate this coefficient using, some ground state properties, okay? And then one does a thermal average of these displacements. In molecular dynamics, one takes a different approach. One calculates this object, basically, at each snapshot, and does the thermal average directly on this object, okay? But if you do the maths, those 2 things should coincide if your system is harmonic, okay? And if it is not harmonic, clearly you need to go to higher order in perturbation theory, but mathematically, at least in the limit of large temperature, these 2 things should be equivalent. Now, maybe I'm going to skip that, but what I want to say basically is that if you go to, if you want to look at probability distribution of the nuclei in a system, okay, if you are a large enough temperature, this probability is Gaussian around the equilibrium site, okay? And the most important thing is that this Gaussian basically becomes broader as you go to higher temperature. So this is consistent with the XRD measurement where you see, the thermal ellipsoid. So if you do look at nice XRD measurements, they don't give you just the crystallographic side, but also the ellipsoids telling you basically what is the mean square displacement of these objects. And this mean square displacement is increasing with temperature. The important bit is that what matters for thermodynamic equilibrium is the average of this quantity, not what happens in the tails. So if you do molecular dynamics and you find something crazy, that's just because you're looking at the tails of a distribution. So it just means that you need to increase your, the time averaging, okay? Because you found some statistical anomalies, and you just need to average over more samples, okay? So strange values of kind of bug structures of gaps in molecular dynamics, they just mean bad sampling, okay? They don't mean that the system is doing something phenomenal. That's basically one of the messages. And finally, this is just the take-home messages. I think the most important message is that for most things that we need to do with electron-phonon physics, we can really go back to the books and look at perturbation theory. We can rederive most of the equations, very simply. So there is not much work needed. Really here, the only issue is that if you want to do a real calculation, there are a lot of technical complexities they want us to learn about, and that's why we're doing this school. But the main concept is very simple, and it's contained in that, okay? So that's basically all I want to say, and you will find some of the references here. So we'll try to give in these lectures the reference at the very end. You don't need to take them because, note them down because we have everything online. So you'll be able to download the presentation and look at it if you're interested, okay? So that's basically the end. And if you have any questions, maybe we have time for a question or something or two. Otherwise, you can meet at the coffee break and you can ask me.